We have just measured the calcium hardness, and now we are going to measure the total hardness, remembering that hardness would be caused by not only calcium but also magnesium and many other multivalent cations, such as, for example, iron or zinc or chromium. So we already have a sample, and what I'm going to do is see if there is any hardness already in the water which I'm going to be using. So I'm going to go ahead and put somewhere between 20 and 50 cc's in the titration dish. Once again, this titration dish is dedicated for hardness because we don't want to have any traces of phenolphthalein. For example, in this particular titration dish, we used it for chlorides and alkalinity. There's going to be always a trace of phenolphthalein that is going to make it very difficult for us to recognize a blue and the total absence of a purple color. So here is the deionized water for the reaction to take place. Now we are going to add versenate hardness buffer solution, approximately 10 to 15 drops. And now the indicator. It's also in liquid form. I put 12 drops. Anything between 10 and 15 drops is fine. And here we can see very clearly that we have a very dark, intense blue. This clearly indicates the absence of calcium, which means that my deionized water is of a very good quality, and I don't have to worry about scavenging and eliminating the calcium to zero the solution, so I can distinguish very well the calcium that I'm going to be having in the filtrate. So now it's time for me to go ahead and add a sample. I'm going to go ahead and measure 1 cc and put it here. 1 cc. And we can already see a very pronounced color change. You can see that this solution is losing its blue and getting some other color which looks kind of brownish with a touch of orange. But anyway, we do not have a pure blue. It's time for me to titrate to measure the amount of cations that are giving off all this hardness. And I'm going to use, again, versenate hardness titrating solution. I'm going to use the intermediate concentration, which is 1 milliliter equivalent to 20 equivalents per million. I'm not going to use 2 or 200. I don't really know how much calcium I have, so I'm going to be cautious using the intermediate concentration and try to get to the final point. This is a 5 milliliter pipette. I'm going to get exactly 5 cc's and start. We can see the tendency for the blue color to reappear. Still a trace of purple. Still a trace of purple, but we are very near. And this is the final point, and I'm reading here 0.7 of a milliliter. That's a very small amount, and as a matter of fact, I can use the calculation that I have 0.7 times 400, which is going to be 280, divided by the size of the sample, which was 1, so divided by 1 would be 280 milligrams per liter of total hardness expressed as calcium equivalent. That makes a lot of sense because usually the total hardness is going to be a number equal or slightly higher than the calcium hardness, indicating that yes, in the fluid we have calcium, but we have some other ions, probably magnesium, giving us some extra reading for the total hardness. So the total hardness comes as 280 milligrams per liter calcium equivalent.